Welcome to Dr. Jimmy's Applied Calculus. Ready for Section 3.2. Again on limits, but looking at continuous and the piecewise. Continuous functions. To start off with, we looked at the word continuous for functions and graphs. If we take a function y equal f of x, and we want to take the limit x approaching some value b of f of x. So we looked at this. If we approach b on the curve, we expect it to approach some value here. In this picture, a nice continuous curve, no jumps, no holes. That expected value is exactly what the function value is. So that's our definition of continuity. So continuous at x equal b is the fact that we have a limit as we approach b left and right, and that exactly coincides with the functional value. Then we get a continuous graph picture. So that's not true of every graph and at every value. But if we look at most of the usual definitions that are taught and used up to a certain point in math and different places, those definitions represent continuity. So most of the things that you're introduced as definitions or expressions defining functions have this continuity property. So what can we do with this? Well, now we want to compute the limit at a point of continuity. can be done for continuous functions at a point by simple function evaluation in many cases. Some examples: if you want the limit as x goes to 2 of the square root of 3x plus 4, this is a nice defined function where it's defined the square root as long as we take a non-negative number, and so we could evaluate the expression at 2, getting square root of 10, and that's the limit. So many nicely defined functions. We know the curve does not have holes, jumps. It's a nice continuous curve. We can just substitute the 2 in this case in to the expression and evaluate the limit. Or something like the limit as x approaches minus 1 of 3 over 4 minus x. So 3 over 4 minus a minus 1. Evaluation gives us 3/5. So most of the time things are defined in a continuous way, and so limits are merely function evaluations. But many of the real world interesting cases are those anomalies where this doesn't happen. So we'll get to that later. But right now, at least, many things compute the limit, it's just substitution. One place that we run into possibility of not being able to just directly substitute would be when functions are defined in a piecewise way. Of course, we have the boardroom type of presentation of something like profit, which has nice, in many cases, straight line segments, so each piece is a nice known continuous function and then spliced together. So in between the splicing, we should be able to just evaluate the function. To look at continuity at the splice from the definition, we'll have to investigate those further. Now, we have a nice way to piecewise define a function. So we set up in a brace the cases. So we might have a nice straight line, y equals 3x plus 7, but we define that only on one part of the line, so only on a particular interval, in this case x less than or equal to 1, and then we continue and may have many intervals making up the line. Here we'll just have 2, so x less than or equal to 1, and then the rest of the x's greater than 1. Where now the new piece has a new definition. Each piece, 3x plus 7, 4 minus 2x squared, is a nice continuous function. It's the problem when we splice them together, what happens? So a limit away from the splice, such as x approaching minus 1 of f of x. Well, we have to look at the case. X getting close to minus 1 would be in this interval x less than 1. So near minus 1, it would take on the value 3x plus 7. If we look at that, then we could evaluate and get a limit of 4. Or if we took the limit as x approaches 2 of this function f of x. It's away, 2 is away from the splice at 1. It's close to 2. It's always defined by 4 minus 2x squared. And so in that case, evaluation at 2 gives us minus 4. Away from the splices, nice and continuous evaluation works. So what happens if we look at the splice where x is 1? Near x equal 1, we have to consider both parts. 4 minus 2x squared. If we happen to be bigger than 1, if it happen to be less than 1, it's 3x plus 7. So we'll look at a left and a right limit. So if we stay on the left, or values of x less than 1, if we're always less than 1, it's 3x plus 7. And we would get a limit of a continuous piece to be 3 times 1 plus 7, or 10. And if we look at the limit approaching 1 from the right, on the right side, x is bigger than 1, so we take the part where x is bigger than 1, and the definition is 4 minus 2x squared. And so limit would be 4 minus 2, 1 squared, or 2. So the limit as x approaches 1 from both sides at once, well, it does not exist because the left and the right limit were different. Now, let's look at another example. G of x defined 2 different intervals or pieces. X squared plus 2 if we stay less than or equal to 2. Change the definition. If x is bigger than 2, in that case 12 minus 3x. So, away from 2, it's simply evaluate one or the other of the pieces. Let's investigate the splice again. what happens at 2. And so we'll look at the left side, which just means x is less than 2. So that would be defined by x squared plus 2. Or, if we stay on that, it should look like 2 squared plus 2, or 6. If we go to the right side and look at this limit, that would be the case when x is bigger than 2. Well, now it should be 12 minus 3x. Or it should come down to 12 minus 3 times 2, which is 6. This time, the limit as x approaches 2, left and right, is that common value of 6. Also, in this case, it turns out that it has a limit of 6 at 2, which matches the value at 2, so it actually is continuous.